Let's do checkpoint 6.19. In this checkpoint, they want us to calculate the line integral of f dotted with dr, where f is a vector field y squared, comma 2xy plus 1, and c is a triangle with vertices at 0, 0, 4, 0, and 5, 0, oriented clockwise or counterclockwise. All right. The first thing we probably want to do is figure out our curve C, which looks like will be in 3 pieces. We have vertices at 0, 0, at 4, 0, and at 0, 5. Now that we have those vertices, we need to connect those lines. And after we connect those lines, what we need to do is we need to parameterize them. So we're going to need to know how to parameterize line segments. This is one line segment. We'll call this one C1. We have another line segment. Let's call this one C2. And then finally, a third line segment, C3. Notice that there are arrows associated with these line segments because we want to go in a counterclockwise direction. And so we can say that the original curve C will be a union of these 3 curves that we just drew. They're actually line segments, but we'll call them curves. Now for each curve, we need to parameterize them. Let us generically just think about the parameterization of a line segment between 2 points. Let's say we have point 1, P, that's x1, x1, y1, and let's call that P1 and P2, x2, y2. Now, the line segment between these 2 points, generically r of t, will equal to the first point, P, plus the parameter t times the direction connecting these 2 lines. So that would be P2 minus P1. And we can put x1, y1, x2, y2 in this formula, but we'll just pick it up from when we actually parameterize our C1, C2, and C3. And after we do that, we also have to note that the formula for this integral, or I usually like to call it the working definition for this line integral, will be equal to the integral from a to b based on the parameterization, the function evaluated at the parameterization, which is going to be a vector because the function is a vector field, dotted with the derivative of the parameterization dt. So that is going to be our working definition to solve these integrals. Let's now parameterize C1 and then compute the integral associated with C1. So C1 will be, let's call this R sub 1, and this is going to equal to the original point, the first point, which will be at the origin, 0, 0, plus t times, now the difference between 4, 0 and 0, 0. So the 4 minus 0 will be in the x component, and the 0 minus 0 will be in the y component. So this will give us a parameterization of 0 plus 4t, comma 0 plus 0. So that's a fairly simple parameterization. And by the way, when we parameterize this, this is always going to go between 0 and 1. Right? Now that we have the parameterization for the first curve, let us proceed to integrate that. We're going to integrate this curve. This is going to be an integral. Let's label it C1f dotted with dr. And this will be the integral from 0 to 1 of the function evaluated at this parameterization. So I have a y squared, but y is equal to 0. And then I have a 2 times x, which is 4t, but it's going to be multiplied by 0. And then I have a 1. So that's the vector field evaluated at this parameterization. Now we will dot that with the derivative of this, which is 4 comma 0. And that's the second part, the derivative. And then this is going to be dt. All right. It looks like when we take the dot product, we will have 0 times 4 and 1 times 0. So that's just going to be 0. So this is the integral from 0 to 1 of 0 dt. This is just going to be 0, and we're done with this first curve. Now let's take the second curve. Let's call that one C2. And C2 will be parameterized with R2 of t, and the starting point will be at 4 comma 0 plus t times. Now the difference between this, the x component will be 0 minus 4, so 0 minus 4, and then 5 minus 0. Okay, let's simplify that a little bit. This is going to be 4 minus 4t and 0 plus 5t. And again, this is going to be accomplished as t goes from 0 to 1. Now that we have our parameterization, we need to integrate. The integral c2 of f dot dr is going to be the integral from 0 to 1. Now the y is 5t, so this is going to be 5t quantity squared, and then we have 2 times x, which is 4 minus 4t, times y, which is 5t, plus 1. We will dot this with the derivative of this parameterization, which is going to be negative 4 comma 5 and dt. All right, it looks like we're going to have something to compute here. This is going to be 25t squared times negative 4. So this is, the integral is going to be negative 25t squared times negative 4. So that's negative 100 t squared plus, and then we have 5 times 2. That's 10 times 5 is 50 times 4. That would be 200. So it looks like there's going to be constant 200. And there's going to be t minus t squared. So that's the first part, and then we have to add 5 to this. All right. This is our integral. We could probably stand to simplify a little bit. I'll start off with the 200s. There's a negative 100 minus 200. This is an integral from 0 to 1. Integral from 0 to 1 of minus 300 t squared plus 200 t plus constant 5 dt. So this is going to be 300 divided by 3 t cubed with a negative. So 300 divided by 3 t cubed plus 200 divided by 2 t squared plus 5t. And that's the antiderivative. We're going from 0 to 1. 0 disappears. This is all 100. And we'll put 1 in here. We're going to get negative 100 plus 100 plus 5. So this will just end up being 5. All right. We got 2 down. We got 0 for the first one. We got 5 for the second one. Now let's take the last one. Now let's call that one C3, and we will be parameterizing this line segment from 0, from 0, 5 to 0, 0. So we're starting off with 0, 5 plus t times this is going to be the end 0, 0 minus 0, 5. So that's going to give us a 0 for the x component and a 5 minus 5t for the y component as t goes from 0 to 1. All right, into the integral we go. This is the integral C3 f dr, which is going to be the integral from 0 to 1 of y squared. So that's 5 minus 5t quantity squared, comma 2x times y. We don't really need to write this, but I'll do it anyways because this is going to be multiplied by 0. And then 1. And then we're going to dot that with the derivative of your parameterization, which is going to be 0, negative 5. All right. So in the dot product, the first component will be 0. And the second component here, this is 0 plus 1 times negative 5. So let's multiply that by negative 5. And we'll do a dt. And then we integrate that. That's going to be negative 5t from 0 to 1, which is going to give us negative 5. All right. Our original problem was asking us to find this line integral. And we said that this is equal to the first line integral C1 plus the second line integral C2 plus the third line integral C3. And what did we get? For the first one, we got 0. For the second one, we got a positive 5. And for that last one, we got a negative 5. So it all goes back to 0. All right. All right. As a summary, we're integrating over this curve. This curve happens to be a closed curve. We'll talk about closed curves in a little bit more detail in the next section. It turns out that if you're integrating a vector field over a closed curve and you get 0 like we did, then that vector field must be conservative, but we won't worry about conservative vector fields until later. Meanwhile, we broke this up into 3 different curves, C1, C2, and C3. We parameterized each curve with limits, and then we use this working definition to find the line integral for each one. We got a 0 for the first one, a 5 for the second one, a -5 for the third one. Add them all up, the whole line integral adds up to 0. All right, that's it for this problem. I hope that helps.